Piping vibration small bore connection corrective actions, improving safety and reliability in piping systems. This topic refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. General small bore connection or SBC corrective actions. Small bore connections, SBCs, are susceptible to vibration-induced fatigue, which can lead to failures if not properly addressed. The corrective actions outlined in Technical Module T11 focus on improving the response of SBCs rather than reducing excitation from the main line. While mainline corrective actions, as described in Technical Module 10, can reduce excitation levels and improve SBC fatigue life, the primary goal here is to enhance SBC resilience. The first and most preferred corrective action is to remove the SBC entirely if it is not essential for plant operation. This eliminates the risk associated with vibration on these connections. If removal is not feasible, alternative strategies must be considered. These strategies include design modifications and structural reinforcements to minimize vibration effects. The methodology emphasizes a systematic approach, assess whether the SBC is necessary, explore design changes, and finally consider bracing or clamping as a last resort. This structured process ensures that each step prioritizes safety, reliability, and operational efficiency while minimizing the risk of fatigue failures in critical piping systems. Design change options for small bore connections. When removal of an SBC is not possible, the next corrective action involves modifying its design to make it more robust against vibration. Several design principles can significantly reduce susceptibility to fatigue. First, minimize the mass of unsupported valves and instrumentation by replacing heavy components with lightweight alternatives such as double block and bleed valves, monoflange valves, or blank flanges. Additionally, remove any valves that are not required for normal plant operation, such as those used only during hydrotesting or cleaning, and replace them with blank flanges. Second, reduce the unsupported length of the fitting as much as possible, as shorter lengths are less prone to vibration. Third, maximize the diameter of the SBC to increase stiffness and reduce dynamic response. If replacing the SBC, opt for short-contoured body fittings, which provide better structural integrity. Finally, ensure that any threaded fittings are fully back-welded to eliminate exposed threads, which are common initiation points for fatigue cracks. These design changes collectively enhance the SBC's ability to withstand operational vibrations and extend its service life. Let's see the figure. This figure illustrates the preferred arrangement for a small bore connection, showing how instrumentation should be mounted to ensure optimal mechanical strength and vibration resistance. On the left, we see the instrument and valve assembly positioned close to the pipe wall, minimizing the unsupported span that could amplify vibration. The center view highlights the connection at the pipe's neutral axis, ensuring loads are evenly distributed around the circumference. On the right, the top view shows the recommended orientation of multiple small bore connections, symmetrically placed to avoid stress concentrations and imbalance. Overall, this configuration represents best practice for maintaining structural integrity, reducing vibration susceptibility, and improving long-term reliability of small bore attachments. Brace or clamp installation guidelines. Bracing or clamping is considered the final corrective measure when removal or design changes are not feasible. The purpose of bracing is to reduce relative movement between the SBC and its main pipe, thereby lowering dynamic stress. Effective bracing must meet several criteria: support any mass at the free end of a cantilever in two planes perpendicular to the SBC axis, and ensure that bracing connects the SBC to the main pipe only, never to local structures like steelwork or decks. This guarantees that the SBC moves in unison with the main pipe. The stiffness of the support is critical. If the support is not sufficiently rigid, it will have little effect on vibration response. For low-frequency excitation, less than 50 Hz. Bolted clamps and braces are suitable, but they require periodic inspection to prevent loosening over time. For high-frequency excitation, greater than 50 Hz, welded gusset plate braces are recommended, with thicker plates for higher frequencies. Welded supports must be carefully installed to avoid introducing new fatigue points, and weld dressing or reinforcement plates can help mitigate this risk. A clamp inspection plan and register should be implemented to ensure ongoing integrity and compliance with maintenance standards. Let's see Figure T11, 2 clamp type of support. This diagram shows a clamp type support arrangement designed to provide stable and vibration-resistant anchoring for small bore piping connections. On the left, we see the front view of the clamp assembly securely gripping the pipe, while the right-hand sectional view illustrates how the clamp, angle supports, and instrument tubing are integrated. The notes emphasize key design requirements. The clamps must be lined to prevent damage, angle supports should be pressed and welded to match the pipe profile, and only stainless steel hardware with anti-vibration washers should be used to ensure long-term reliability. The support is fully welded to protect against corrosion. And this configuration is specifically intended for small bore branches up to NPS 50. Overall, the figure highlights a robust support method that minimizes vibration, enhances structural integrity, and improves the durability of small bore connections. Let's see next Figure T11 3 clamp type of support. This diagram illustrates another recommended clamp type support arrangement designed to stabilize small bore connections and minimize vibration-related failures. The left view shows how the support bracket is angled and welded to provide a rigid load path from the small bore tubing back to the main pipe, while the right view highlights the full clamp assembly secured around the pipe using stainless steel bolts and anti-vibration washers. The accompanying notes emphasize important construction requirements. The clamps must be lined with 1.6 mm thick material to prevent pipe damage, angle supports must be pressed and fully welded to match the clamp profile. And all hardware should be corrosion resistant and fully painted for protection. This arrangement is specifically intended for small bore branches up to NPS 50 and provides a robust, reliable support method that reduces dynamic stresses and enhances long-term integrity. Let's see next Figure T11 4 clamp type of support. This diagram presents a reinforced clamp type support arrangement designed to provide maximum stiffness and vibration control for small bore connections. The left view shows the use of multiple angled gusset plates that tie the clamp back to the main structure, forming a triangular bracing system that greatly increases rigidity. The right view highlights how the clamp securely wraps around the main pipe, while the instrument tubing is supported by a dedicated bracket to prevent excessive movement. The scrap view further clarifies the clamp leg geometry used to stiffen the assembly. The noted requirements specify that the clamps must be lined with 1.6 mm thick material, angle supports must be pressed to the clamp profile and fully welded, and stainless steel hardware with anti-vibration washers should be used to ensure durability and resistance to corrosion. Designed for small bore branches up to NPS 50, this arrangement offers a robust solution for minimizing vibration, improving structural integrity, and extending equipment reliability. Let's see next Figure T11 5 two-way welded gusset plate support on unconnected SBC, 2 inches and below. This diagram illustrates a two-way welded gusset plate support arrangement used for unconnected small bore connections of 2 inches and below, providing a stiff and stable structure to control vibration. The upper view shows how a 6 mm reinforcing plate is welded around the branch connection, positioned at an angle between 45 degrees and 85 degrees to strengthen the attachment. The lower view highlights the use of paired 40 x 6 mm gusset plates, also welded at similar angles, creating a triangular bracing system that transfers loads efficiently back to the main pipe. Typical 4 mm fillet welds are used throughout to ensure structural integrity. And all bracing materials must match the parent pipe to avoid differential behavior. This arrangement significantly increases rigidity, reduces the likelihood of fatigue failure, and represents good engineering practice for supporting small bore piping that is not directly tied into the main system. Let's see next Figure T11 6 4-way welded gusset plate support on unconnected SBC, 2 inches and below. This diagram shows a 4-way welded gusset plate support arrangement designed to provide maximum rigidity for unconnected small bore connections of 2 inches and below. The illustration highlights how 440 x 6 mm gusset plates are symmetrically welded around the branch at angles between 45 degrees and 85 degrees, forming a highly stable support structure that resists vibration from all directions. A 6 mm reinforcing plate is also fitted and contoured to suit the curvature of the connection, ensuring even load distribution. Typical 3 mm fillet welds secure both the gusset plates and the reinforcing plate, creating a robust, continuous load path back to the main pipe. By providing multidirectional bracing, this configuration significantly enhances structural stiffness, reduces fatigue risk, and represents best practice for supporting small-bore connections that are not directly tied into the parent piping system. Let's see next figure T11-7, 3-way welded gusset plate support on unconnected SBC, 2 inches and below. This diagram illustrates a 3-way welded gusset plate support designed for unconnected small-bore connections of 2 inches and below, providing strong directional support in applications where the branch is located on a curved or elbow section of pipe. The arrangement uses 340 x 6 mm gusset plates welded at angles between 45 degrees and 85 degrees to create a stiff triangular bracing system that effectively transfers loads back into the parent pipe. A 6 mm reinforcing plate is shaped to match the curvature of the elbow, ensuring a secure and evenly distributed attachment. Typical 3 mm fillet welds are used throughout to ensure structural integrity. This configuration increases rigidity in multiple directions, reducing vibration and minimizing the risk of fatigue failure, especially in locations where pipe curvature limits the use of 4-way bracing. Mitigation strategies for tonal excitation. Tonal excitation occurs when the excitation frequency couples with the structural natural frequency of the SBC, creating resonance and amplifying vibration. To mitigate this, two primary strategies can be employed: altering the mass or changing the stiffness of the SBC. Increasing the mass of the SBC lowers its natural frequency, while increasing stiffness raises the natural frequency. Practical methods include installing braces or clamps to enhance stiffness or shortening the connection length. However, these modifications must be carefully evaluated to avoid introducing new resonance conditions. Experimental modal analysis, EMA, as described in TM08, is strongly recommended to verify that the modified SBC's natural frequencies are sufficiently separated from excitation frequencies. This analytical approach ensures that corrective actions effectively break the coupling between excitation and structural response, thereby reducing the risk of fatigue failure. By combining physical modifications with rigorous analysis, engineers can achieve a robust solution to tonal excitation challenges.